Hi, my name is Tori Martin, and I'm really making this video for my calc-based stats class, but if you do stumble upon this, I hope you find it helpful. So today we're going to be talking about hypothesis testing and looking into a few things. Start here. There we go. All right, what is hypothesis testing? So previously we studied how to construct a confidence interval estimate of a parameter from a sample data. However, many problems in engineering require that we decide which of the two competing claims or statements about some parameter is true. This is at the heart of hypothesis testing, and an example includes things like software testing. So p-values. We've talked quite a bit about these before, but p-values and hypothesis tests. One way to report the results of a hypothesis test is to state that the null hypothesis was or was not rejected as a specified alpha value or level of significance. So essentially what this means is we have a claim and we do an experiment, and then based off of the information that we got from the experiment, we will either accept the new claim or we will reject the new claim. Okay, and so the p-value is the smallest level of significance that would lead to rejection of the null hypothesis, H naught. So again, the null we use as H naught, and we normally use H of 1 to be our new claim. So the H naught would be how things are versus H of 1 would be our new claim. So if we go on to look at an example here, we have a textile fiber manufacturer is investigating a new drapery yarn, which the company claims has a mean thread elongation of 12 kilograms with a standard deviation of 0.5 kilograms. The company wishes to test the hypothesis that the mean is 12 against the new hypothesis saying that the mean is actually less than 12. Using a random sample of 4 specimens, we want to calculate the p-value if observed statistics is where we have a sample mean of 11.25. So again, let me go to draw. So again, this is the original claim, and this is our alternative claim, where our original claim is that it is 12 kilograms versus we are looking into an alternative claim that is actually less than 12 kilograms. We're going to use 4 specimens. So our n will be 4, and we are going to observe that the sample mean value is 11.25. So for this, let's do define p-value. We have p, where we're going to find our z, which is less than or equal to. Right, so we talked about this formula before. I'll write it up here, but it is x bar minus mu over sigma by the square root of n. So let's fill those in. So our x bar here is 11.25. minus our mean, 12, divided by sigma, I don't know what I'm doing that, sigma being 0.5, divided by the square root of, in our case, 4 for n. All right, in doing so, we're going to get P of Z is less than or equal to. Now, if we do all this good stuff here, we are going to get a -3. Okay. Now, if I go to my sheet here, and I plug in my data value, which we got is -3. We will see that, right, is going to be this guy right here. And we want the left probability because we're saying that Z is less than the value that we're finding for. So since we're trying to find less than or to the left, we want that left probability, which in our case is 0.00135. So our probability of if the mean is 11.25 would be 0.00135 as our probability. Okay. All right. Let's move on to type 1, type 2 errors. So in this, obviously errors can occur. So we can have a type 1 error is when we reject the null hypothesis when it is actually true, and type 2 error is failing to reject the null hypothesis when it is false, which is called a type 2 error. And then here's a little decision factor. So we fail to reject the null if H0 is true. There's no error, but then we make a type 2 error. We will reject the null if we make a type 1 error. So if we look here at example 2, it says a consumer products company is formulating a new shampoo and is interested in foam height in millimeters. Foam height is approximately normal distributed and has a standard deviation of 20 millimeters. The company wishes to test the null hypothesis being that the mean is 175 millimeters versus that an alternative claim that is actually greater than. So in this case, we're looking for the right probability because we're asking for that is greater than mu, versus in the previous example, we wanted the left probability because we said it was less than mu. And we want to use these results for n samples, and so find the boundary of the critical region if the type 1 error probability is alpha is 0.01. And so for type 1, we normally use alpha, and then for type 2, we use beta. And we're going to have n is equal to 16. So to begin here, let me just switch back to red. All right, so to begin, we want to find this boundary. So in order for us to find this boundary, we need to figure out where is this x bar going to be. Well, obviously, we are hoping to find that it is greater than or equal to 175, because that is what we are looking for with our claim. And for this boundary, it'll need to be 175 plus our z alpha, our critical, of 20 over n, square root of n, being our formula, where 20 is our standard deviation. Now we can plug in the given values that we have. We know that alpha is 0.01, but since we are looking for greater than mu, I'm actually going to do 1 minus 0.01, which I know that will get me 0.99. This is what I'm going to plug into the calculator, or my Excel calculator, to give me what my z value would be. and we are going to multiply that by 20 times the square root of, in our case, 16. So let's go ahead and plug this in. Okay. All right, so here, all right, so we are going to do, in this case, we want to use given the left probability. So if I plug in 0.99, I'm going to be given a left probability of 2.32. So that is what I'm going to use. And we know that's going to be, in our case, 175 plus our z alpha over 2. So I'm going to put a parenthesis, 2.32 times 20 divided by the square root of n, which is 16. And that should give us 186.6 being our critical region for this type 1 probability. So our critical value is 186. Okay. All right. Let's move on to talking about power. So our probability of a type 1 error is where we have alpha is a type 1 error where we reject the null and when the null is actually true. A type 2 error is when we fail to reject the null. So we should have rejected the null when the null is actually false, but we ended up accepting the null. So that is a type 2 error. Now, an important concept that we use is power. So the power of a statistical test is the probability of rejecting. So we're trying to find what is the probability of rejecting the null hypothesis when the alternative hypothesis is true. So power can be calculated by doing 1 minus beta, and power can be interpreted as the probability of correctly rejecting a false null hypothesis. So what's the likelihood of me doing the right thing when rejecting a false null hypothesis? So let's jump here to example 3. Here we have a manufacturer is interested in the output voltage of a power supply used in a PC. Output voltage is assumed to be normally distributed with standard deviation 0.25 volt, and the manufacturer wishes to test the null hypothesis being that it's 5 volts against that it's not 5. So our alternative, we are saying that is not 5 when originally our original claim is that it is 5 volts. And here we're going to use a sample of 8 units. So for part A, we want to find the acceptance region is 4.85 is less than or equal to x bar, which is less than or equal to 5.15, and we want to find the value of alpha. So in order to do that, let's define some things. So first, what is alpha? Well, alpha is going to be the probability that we have x bar is less than or equal to 4.85 when the mean is 5 plus the probability of that x bar is greater than 5.15 when the mean is 5. When mu is 5. So to begin to figure this out, let's start plugging in. So again, we want to use the formula that we've been using where we have x bar minus our population mean, which is 5, divided by our standard deviation, which in this case is